Good morning, everyone. I'm Yuezheng from Beihang University. I'm happy to share our recent work, HyLink, harnessing PCIe and dedicated interconnects for efficient collective communication. How to switch the next? In recent years, LLM parameter scale continues to grow rapidly, which requires increasingly large-scale training clusters. To support this large-scale distributed training, several parallel mechanisms are applied, such as data parallelism, pipeline parallelism, and the tensor parallelism, which means frequent synchronization of huge data volumes by collective communication. Some of this communication, such as data parallelism, can be overlapped with communication, with computation. But much of this communication, such as TP or EP, the expert parallelism, is exposed on the critical path and not overlappable with compute. And studies on real LLM training report the TP communication long can reach 22 to 47% of iteration time. So optimizing collective communication is essential for LLM training. To optimize collective communication, we have the following two observations. First, we find current CCL has a topology mismatch for PCIe machine. It affects many cost-efficient machines which adopt the pure PCIe topology without dedicated link. Existing CCLs, for example, Nickel or MSCCL, model this PCIe topology as a flat GPU to GPU network, which mismatches the underlying CPU-centric PCIe tree topology. They treat the CPU as a passive relay and causing redundant PCIe traffic. And here is an example of two NIMA 4 GPU algorithm. For Nickel's ring algorithm, a 4-rank algorithm needs 3 steps, so each GPU upload and download 3 chunks from peer GPU. For interneumal link, it also transfers 3 chunks each direction. But theoretically, for algorithm, a rank only needs to upload its own chunk, and the interneumal link only needs to transfer data of peer numerous ranks, which is 2 here instead of 3. The other observation is when the machine equipped with dedicated link, the vendor CCL often leave PCIe link idle. When a dedicated link exists, they route all traffic through it and simply ignore the PCIe path. For machines that have dedicated link, for example, NVLink or SGMI or HCCS, the idle PCIe link can add 10 to 32% of extra bandwidth across hardware vendors and generations. Furthermore, PCIe is vulnerable to interference. For example, checkpointing, data loading, or monitoring, all of them consume the PCIe bandwidth. So the available PCIe bandwidth varies at runtime, and runtime reduction is needed. Based on the two observations, we propose HyLink, a two-layer collective framework to make better use of PCIe bandwidth. For observation 1, the PCIe topology mismatch, we propose PCIe CCL, which models the PCIe hierarchy natively with the CPU as an active router and compute node. For observation 2, aggregating the PCIe bandwidth in dedicated link machine, we propose the multipath orchestrator, which split collectives and make them run on both the dedicated link and the PCIe link efficiently. The workflow is when a collective task arrives, it will be intercepted by our library. And if the machine doesn't have dedicated link, the task will be sent to the PCIe CCL. Otherwise, the collective will be separated into 2 paths according to a speed ratio alpha and send them to the PCIe CCL and the vendor CCL separately. The multipath orchestrator will record the execution time of both types. The first is PCIe CCL. To include CPU into collective communication model, we propose a CPU-aware collective domain-specific language. It illustrates how data flows in a PCIe topology in a chunk granularity. The DSL includes 3 types of instruction. The first is D2D, which can place each rank's own contribution in its receive buffer in the same rank. And then in D2H and H2D, it moves chunk between a GPU and its local host memory. The last type is H2H and reduce. They route chunk across Neumann nodes or reduce them in the host memory. The question is how to choose the chunk granularity. If we use too few chunks, we will suffer from insufficient pipeline depth and finally leave large bubbles. Otherwise, if we use too many chunks, it will create too many instructions and make the algorithms harder to write. So to address this dilemma, we propose an auto pipeline transfer engine. And the right-hand side demonstrates the subchunk data flow of a PCIe algorithm. It keeps the DSL at chunk level, but moves data in subchunk granularity, which allows the D2H, H2D, and the host side stages to overlap in a full duplex pipeline. And it automatically computes the causal scheduling and enforce the dependencies of D2H, H2H, and H2D. That means a subchunk can be transferred to the next stage only after it arrives. The second component is multipath orchestrator. It enables the multipath collective communication on both dedicated link and PCIe link. It first split input and output the logical chunk into 2 parts and send them to the PCIe CCL and the vendor CCL, such as Nico or Hiko. To guarantee the correctness of a stream semantic, we use stream with event API to make the PCIe CCL and the vendor CCL, these 2 streams wait on the user stream, and on the collective compilation, make the user stream with these 2 streams. And after collective communication completes, multipath orchestrator measures the 2-path execution time and adjust the splitting ratio of the alpha. For example, when PCIe link is occupied, the ratio for PCIe task will be decreased for the next iteration. When the PCIe link becomes idle again, the ratio will increase back. We implement HyLink as 2 library, about 6,200 lines of code for PCIe CCL and 4,600 lines of code for multipath orchestrator. And the code is currently available on GitHub. We evaluate HyLink on 2 types of machine. For PCIe-only machine, the PCIe CCL can improve the collective bandwidth by up to 2.28 times compared to the Nico. For dedicated link machine, HyLink can improve collective bandwidth by up to 1.4 times compared to the Hiko, which uses its dedicated link HCCS alone. We also evaluate HyLink on simulated PCIe interference. And HyLink can improve throughput up to 66 compared to the split ratio. To summarize, the PCIe bandwidth in GPU clusters is currently underutilized for collective communication, and HyLink unlocks it through a 2-layer co-design. The PCIe CCL model CPU as an active router and reducer to eliminate PCIe redundant traffic, and multipath orchestrator aggregate PCIe and dedicated link to execute collective communication. And there are some directions for the future work. First, we consider to implement the topology-aware DSL synthesis because the PCIe layout may differ across machines, but they share a common tree structure. So one synthesizer may generate the best DSL for any platform. The second thing is intra-iteration work stealing. Once the dedicated link finishes, it can steal the PCIe path residual chunks, which can cut in the rebalancing time from several iterations to within one. Thank you for your listening. I'm happy to answer questions here or by this email.
We have time for questions. Please.
Nice work. Have you considered the interference between different traffic using the same subset of the mask?
Currently, we just use another process using the Coleman-Copia sync, the host device to simulate this interference. In the future, we consider using the different type of the interference.
So how to control the interference? So what kind of congestion control algorithm or something like that?
I think the PCIe interference is not easy to control because we simply just use this link to work, and there is currently no the control method of the bandwidth.
Thank you.
Any other questions? Yes. So let's thank the speaker again.
Thank you.
Thank you, Yuezheng. So the second paper is also about communication collectives, and the second speaker is Fei Long from Tsinghua University. Fei's research focuses on networking for AI. He has worked on networking systems, network simulators, and AI infrastructure. Fei, please.